In this video, I'm going to discuss the questions number 2 and 3 from your lab sheet 6, based on a request from from few students. So let's look at question number 2 first. So I'm just going to give you sort of the the codes that you'll be using in Octave and the procedures approach that you need to follow so that you can apply this on your own. So let's start with question number 2. We find that it's a unity feedback system. And the first step, we're going to create that plot there, which is 1 over s plus 1 times s plus 2 times s plus 10 as a transfer function first, and then we can first part the root locus. The first part is asking us to find the operating point with a damping ratio of 0.174. So we would be putting overlapping the damping ratio line on the root locus and then finding the point of intersection. So let's Octave and see how it is done. Now, once you are in Octave, we know that you need to load the control package. So before we've done that, if you want to use any functions that are available in Octave, which is from the control toolbox, then you need to load it. Yep. So I've done that already. So you need to load the PKG, this one PKG load control. So you need to run this command, and then you are able to use functions PS or step or other functions. I'm not going to run this one now. I've done it already. Now, the first step will be to create a transfer function. Let's do that. We use F, and we found that it is a 1 in the numerator, so there's 0, and then the denominator is s plus 1, s plus 2, and s plus 10. So I'm using the poly function there to create your denominator. So it's -1, -2, and -10. Okay, so this you should be able to get. Yep, transfer function, just as it is. And then let's just run the rlocus command. So this is what we're getting. Okay. Now, next step here, let's overlay your damping ratio line. We know the damping ratio is 0.174, so we want S with 0.174. I've said earlier, let's just use a very small value for natural frequency value. If you put 0, sometimes it can lead to problems. So if we just overlap here, we look now at our root locus, we find our damping ratio line overlapped on the root locus, and then this is the operating point. So let's just now zoom onto this. You can use input to get that point, but a very simple way is just to zoom onto that and then just place your cursor on that, and then just read the value on the left-hand corner. So you find this -0.69269. And then the 3.9221 is the imaginary part. So you already have the operating point, just can take note of that. So the operating point at this point in time, the intersection between your damping ratio line and your root locus is 0.69269, and then 3.9221. It's plus, so the second value, like I said, is the imaginary part. Okay, now the next task will be to find the gain at this point. Now, again, if you're using MATLAB, we get it directly from all sides, but to help you to find the gain at a given operating point on the root locus, I've sent you one function called rlocus gain. So I've sent that to you, and you can use it. So first, on my computer, it's stored on that active folder here, MATLAB code. So you need to find out on your computer which is active folder, make sure it is there. Then just type help rlocus gain. So if it's recognized, you should be able to get the help, yep, the help documentation. So just to give a brief on that. So the rlocus gain function takes the poles, the zeros, and the T here is your operating point. Yep. And based on this, it's going to calculate the gain K. And the function also returns sum of angles, which is quite interesting. If you need to design, for example, PD controller, and you typically need to find the sum of angles at a given point, again, for specific operating point. So as we go along, we will use the same function there to find the sum of angles. Yeah. So let's start first is create the P. So what are the poles from the open the poles of -1, -200 calculated current bacteria. Yeah. This is how the function works. So this is your P. Now the Z is just an empty variable because we don't have any zero here, and the T there is your operating point, which we just noted to be 0.69269, minus 0.69269 plus 3.9221i. this is your operating point, and if I just copy that here and just call a function, we should be able to get to k. So at this point in time, we get k is 164.28, and you can find the sum of angles is very close to minus 180 degrees expected, because that's what is on the root locus. We've seen before all points of the root locus is from an angle of minus 180 degrees, so it's very close to that. It's accepted. So of importance for us here, we are not running this, we're not calling this function to get a sum of angles at this point, because we know to minus 180 degrees. We want to get the gain k. Why? Because the gain k is going to decide actually that you're operating at this point that we just selected. Now, if you look at the question now again, so show the locus points the complex temperature ratio line, hence find the point in the root locus for the system will operate at temperature ratio of 0.174. We've done that by reading it in Octave in the lower part. Now, if we want to calculate the peak time and stepping time, it means we need to call a step function. Now, be careful when you call a step function. It means you are calling a step function. This is a step input. It needs to be fed to your closed loop transfer function, which is g over 1 plus gk. So 1 over 1 plus gh. In this case, your h is 1. Yep. So, but of course, you have to multiply this g by k, and we have a value of k over. Now, how we do that in Octave? It means we need to find a closed loop transfer function, the gc. Let's call it gc. It is g times k. Yep, it is g over 1 plus gs, but your g is always g times k over 1 plus g again, but g is again g times k, and then the h is 1. So you can just leave it like this. So this is your closed loop transfer function. Now, if you call the step command now on gc, this is what you're getting. Yep, so this is your step input. Yep, and you get a variation like that. Now, if you look closely at the system we have, we can find the type 0 system. Yes, a type 0 system. So based on the theory covered in steady-state error, a type 0 system would have a constant error for step input. This is why you find that the value of the final value that the step response is going to is not 1, but you have an error there. So you can work out this error using your KP, and then your steady-state error is 1 over 1. So you can work this out. For the first part, you find that you want to determine the peak time. So how we find a peak time, just have to hover your cursor here, or you can zoom a bit in if you want, and then more or less it's here. So we find the peak time is around 0.9 or 0.897. Yep. So you can just pick that up. And then if you want to find a settling time now, so to find a settling time, it's important here that you find this steady state value, because the settling time is the time which the step response takes to be within 2% of the final value and stay within that 2% band. Means you need to know the steady state error. Now, how we find that? It's pretty simple. You can just work out we can do that on paper, yeah, because we don't have a DC gain function in Octave, so you can just work out KP as the limit as s tends to 0 of ds. But of course, you need to multiply by k, because you can find here, and you already know the value of k. So if you plug it there, you can get your steady state value. And then based on that, you can look on your graph now. You can zoom in at where it is stabilizing here. So at what point it reaches personal final value. Yep. So let's say the final value it is tending to 0.9. Just to take an example, I just go on the right there. You find that it is still oscillating, but you can get a steady state value. Yeah. And then once you have a steady state value, you can determine at one point it stays within 2%, and then take that value for the second time. So this can be easily done. Okay, so this part is okay. Now, next part is determine the steady state error of a systematic temperature ratio of 0.174 where step input applies. So we've done that above. Yeah, so you can just work it out manually by finding your KP and then just plug into equation 1 over 1%. Okay, now determine the steady state error when a pole is placed at the origin. Now, if you place a pole at the origin, what is actually happening? You're increasing the type of a system, which is now a type 1 system. And if you do the step, if you apply step input to a type 1 system, expect the error to become to be the steady state error to be 0. Yeah, so we can do that. And then we want to sketch the new root locus. So basically, we need to modify now your G. Yep. Or if you want, you can create a transfer function just for 1 over s and then multiply by G to get a new transfer function. And then we can sketch. Now, can the transit response of the system be maintained? Normally not. We know when we place a pole at the origin, it totally disturb the it totally disturbs the root locus, and it means you're not able to achieve the same transit response, even if the stated error is expected to become zero, but the transit is not maintained. So if not designed stable control so that the initial transit response is obtained. So this is where we can place zero very close to origin and then observe whether you are still getting more or less the same step response. Sketch the root locus, obtain and validate the same overshoot, peak time, and setting time are achieved. So if you have placed that zero close to the origin and then you invalidate, if you get more or less the same step response, then you can say that you have achieved the function, if you want, the objective of getting zero state error, but yet maintaining the same transit. Let's do that Octave. So we already have our. I'm just going to close the now. Yeah. So we already have our G. Our G was defined already. Now, what are we doing here? We are including in that G an S. Yep. So you can do it in that way. You can call how we define G before. Yep. So it means in the numerator now, in the denominator, you're going to add a zero here. Yep. It's one way to do that. And if you want, you can call it another let's call it G1. So we know G1 is the transfer function where you have placed a zero at the origin or at the origin. If you look at it now, so you can see you have multiplying S in the denominator. Yep. So if you call the locus now, the root locus would be, of course, very different now. Yeah, because you have added this. Sorry, I've called R locus. That's correct. I need to call R locus G1. Yeah, this is a new one. Okay, so your root locus is very different now. Now, if you overlay on that again, your damping line, so it's with 0.174, and then small value for the damping rate for the natural frequency. So you have your line there. If you just zoom in again, you can follow the same step, find where actually your root locus is intersecting the damping range line. Yep. So you can follow the same step. And so we are getting now a minus. So your operating point now is minus 0.1624 plus 0.92172i. So if you compare what your operating point was earlier, which was minus 0.69269, now you're at minus 0.16264, and the imaginary part earlier was 3.9. 1i, and now it is 0.92172. So definitely operating point has changed. So your transit, we know the transit response is heavily dependent on the operating point. If you want, you can follow the same step we've just done. So you have the operating point now, the new operating point. So we can just write it down as T again, or if you want, you can call it T1. The new operating point is at minus 0.16264 plus 0.92172i. Yep, so this is your operating point you're getting now when you place on the pole at the origin, and you can call again your K. Yep, if you want, you can put K1 there just to differentiate. You have the same P, the same poles, but you have to be careful now. We need to create, because now you have another pole. Yep, you have another pole which you created. Remember, you have added a pole, so let's just add a zero here. Yep, because you've added a zero at the origin. So this is your poles now. Yep, so pole of your system. The zero is the same. We had it as an empty. And your target point here, which you're calling T1, is already defined. So if now, okay, so when you call now your R Lucas gain function with PZ and of course T1. So T1 is a new operating point of gain, which is minus 0.16264 plus 0.92175. So you get your moment close to minus 1 degrees. Again, as expected. I've just take note of that K1 here is 23.672. Now, if you want to find now the step response for these 2 points, as expected, it should change. So let's try to overlay both response on the same graph. So we had GC already calculated. Remember, we have calculated GC already. Let's take some time. Yeah, so we already have GC. Yep, so GC was calculated earlier, and we have already included the gain here I'll get the early gain k. Now, if you want to find the GC2, yep, the GC2 is going to be your, if you see, we have defined already G1. G1 had a pole already, the pole at the origin, so at G1. So it's going to be G1 times G1. Same formula we've used before, but just be careful, don't mix things. Now you're using G1 for including the pole at the origin, that's the first thing, and the corresponding gain is G1. Yep. So this is the new closed loop construction. Yep. Again, your H is again 1. This is why we don't have anything for H. So this is what we get for GC2. If you just step of these two, so step of GC as we see earlier, see what you obtain. If you now just hold on, instead of plotting on the same graph, if you just step of GC2 now, so you find your response is different. Yep. So this one, you had an initial one, and you're getting now a different response. So as expected, your response will be different now. If you compare the two responses, remember your operating point, the new operating point has a lower, has a much lower real part. You expect your settling time to be moved down. Absolutely, this is the new one you get there. Let me just try something. Step of put that. Yes, you can put it in red. So this is for your initial system, and then we just say on, and then we call GC with GC2 now, and let's put that in. So you should be able now to find the difference. Yeah. So the blue one is the what you're getting just by placing the pole at the origin, and as expected, the transit has totally changed. Even if your steady state error now, if you look at the steady state error, it is 0, yeah, because our system is of type 1. Yeah, but the transit has been disturbed. So this is for our initial G1. Yeah, and I'm just putting this one into G2 now, just not to confuse. G2 is you added also 0 at minus 0.1. Yep, so this is our locus on G2. So now you find that your root locus is more or less how it was before, as we know, because now your pole and your 0 are very close together, so you expect to get more or less the same form for your root locus. Yep. So next step, let's overlay on that grid as grid 0.174, comma 1, as we done earlier, and then we just get the new operating point. So I'm just going to show you the new operating point, and then we can follow the same step to validate whether it's a closed transit or not. So the point we're getting now is the new operating point with the pole at the origin, but also 0 at the closed origin at minus 0.1. So we're getting minus 0.7408 plus 3.8309. So if you compare this point to the very first operating point we had, it is very close now. It won't be exactly the same, but it's very close. So now you can just do the same step. If I just go to your lab sheet now. Yep. So you can do the same step now. You can find the gain k using your R locus gain function, and then you can use that gain to create a closed transfer function with your new transfer function with a 0 close origin and a pole at origin, and then you can just step. You're going to find, then you can validate whether it's close or not. And then you can plot the step response with and without compensation. So now you should be able to do that. The important takeaways from what you've discussed here is you are able to plot a root locus, to overlay a damping range line, find the operating point, and also find the gain at this operating point using the R locus gain function. And then once you have a gain k, you can just find g over 1 plus gh. In this case, our h was 1, but be careful, your g is not g, is g times k. So the k you found already. So basically, it's g times k over 1 plus g times k. And then if you've got a closed transfer function, you're able to do step response. And from the step response, you can very easily find parameters like peak time, settling time, and so on. Okay, so let's try now question number 3, which is very similar. So question number 3, if you look at the transfer function now, it's type 1 system because you have an S in the denominator, and in this case you find it's still a unity feedback system, but the gain k is inside the transfer function. It doesn't matter, you can put it outside, but in this case it's shown here as a part of the transfer function. If it's not shown, it's just 1 over s equals s plus 4 times s plus 6. You need to assume that k, because this is what's varied when you find your root. So again, I'm going to shift to Octave now. What's mentioned is you want to design an ideal derivative compensator. So I'll just show you the different steps to help you design that. I'm going to move over that extensively in theory in your lecture slides. So I'm just going to show you the main steps, how you do that in Octave. Okay, so first thing you need to do here is you are given the overshoot is 16%. So since overshoot is 16%, you can find the damping ratio first. The damping ratio you can find because overshoot is exponential minus I prime over square root of 1 minus I, 1 minus I squared. So you can work out the damping ratio from this expression. You're going to get 0.50387. So we can use 0.504 as a damping ratio. So let's go to Octave now, and I'm going to clear everything first. Yeah, the screen. So let's create now our transfer function G. So it is again, I'm going to use poly. So in the numerator it is 1, and the denominator we can use poly, or you can use convolution if you want. So we already have one pole at the origin, and then we have one pole of -4 and one pole of -6. Yep. So this is what the transfer function is, and immediately we can do our locus. This is your original uncompensated system. This is how your root locus looks. Yep. So next step, we can overlay on that your damping ratio line. So as I said, damping ratio of 0.50387 corresponds to a 16% overshoot. So you can work this out from the formula. Then we use 0.01 against natural frequency because we compute like that. So this is what we have now overlaid on that. So again, just going to zoom quite closely on that point, and then just put your cursor on that point. Yep, as close as you can, and then just note down the operating point. So I'm getting -1.036 plus 2.0624i. Just note this down. Yep. So I'm getting an operating point of -1.2036 plus 2.0624i. Yep. Next step here, again, we're going to use the R locus gain function to find the gain at this point. So I'm just going to create first your operator target point or operating point. So we've said it's -1.2036 plus 2.0624i. Yep. And then if for this question, again, your Z is at 3 because you don't have a 0. And your force now would be at 0. You have 1 at -4 and you have 1 at -6. This is your vector for your force, and then let's call again your K and sub angle. I'm just going to call it K still, and we have to use 31, but yep, we are starting. So again, your sum of angle is very close to -20 degrees because that point is on the root locus. So you get your K and K as 43.320 here. Yep. Just like we've done, you can find your closed loop transfer function. You see is equal to G times K over 1 plus G times. Yep. So you get the closed loop transfer function, and now you can call your step on which the step function on that closed loop transfer function, and this is what you're getting. This is your step response. Now the question asks you to find to design an ideal derivative compensator to use 60% overshoot. So you want to the same transient at 16% overshoot, but you want to reduce setting time by 3. Now it needs you to find setting time. If you look at the step response here, and as we expect, the final value is going to 1 because it's type 1 system, and the step response for a type 1 system is going to have a 0 steady state error, means the output would tend to 1. So how you find the settling time now? So I'm going to illustrate that here. So you want to find when first the system reaches within 0 point, because you want it to be in a 2% band, remember, so either above or below. Now, if you look at the response here, if I just zoom out again, so you find that the response is up, and then it doesn't get anymore, and then it's stabilizing at 1. So most likely your setting time will be somewhere here. So what we need to do now is just to zoom in here and find where you get 0.98. You just look at the down. You find here you have a point which is very close to 0.98. You can just as close as possible. So I think this is good enough. So you can just something here. So it means around 3 points. You can say your settling time is 3.548 if you want seconds. So you've got your settling time here, based on the first point at which you reach 0.98 of the final value, and then you stay within that. A very important consideration for settling time. And once you have that, then you're going to follow the same step. You're going to find out a new operating point. This has to be done by hand now. So this is elaborately discussed in your lecture slides. Once you have a settling time, you would find a new settling time as 3.548 divided by 3. So you get the new settling time. From the new settling time, you find the new real part. So the settling time is 4 over the real part. So you have a new settling time, a new real part. And then since you're operating on the same damping ratio line, you just have to find a new imaginary part. So once you have the real imaginary part, you have a new operating point. Now the good thing is, remember, when you have a new operating point, you need to find the sum of angle at this point. You can use the R Lucas gain Remember, when you're holding the R Lucas gain, we get the gain here. You also get the sum of angles. So when you find the sum of angles at the new operating point, it would not be minus 1 degrees because it's not yet on the root locus. So from the value that you're going to get, you can decide what angle is to be added by the field controller to be able to make the root locus move to that point, and then you follow the same step. So then you size you find the location of that 0, which is the PD controller. Then from once you get that PD controller, then you create a new transfer function, you multiply it by your original plot, and then you follow the same step. You put a new root locus, you overlay the damping ratio line, you get a new operating point, you get the gain. Okay, and then you just have to again plot the step response, and then you can just validate it. So this is following very similar to what we've been doing question number 2. We should be able to do that because it's a very similar skill set, but except here we are designing the PD controller, but most things should be done on paper, which you should be able to do once you've got the so just maybe to illustrate, when I did that calculation, I've got so I followed the same step I've said to you. I've got the setting time was 3.548, and then divided by 3, you get the new setting time. From the new setting time, you get the new real part. From the new real part, by trigonometry, we know we can get the new imaginary part. So you have your new operating point defined, and once you have this new operating point defined, you can find the sum of angles. So I've got the sum of angle of I just look at it, of minus 270.25, and then and that means you need to provide an angle of plus 90.248 degrees to be able to make the root locus go through the new operating point. So when I've got 90.248, and then from this angle I've calculated the 0 that you need to add to the PD controller. I've got 0 of at minus 3.3 at minus 3.37. Yep. So let's just do that now. It means my G of PD is at let's put the transfer function for it. So it is of course the PD controller is having a 0 in the it could be the numerator. Yep. So you have S. I've got S plus 3.37. So you get out the numerator is 1. Yep. So this is your PD controller. I can see it's just there's no denominator here because it's 1. So this is what is your PD controller. And then if I create now Q, I call it Q. Remember, you're taking your original plot, which was G. Before we go to that, let me just show you your G. So this was your G, and now you're taking your G multiplied by G PD, which you just created. So I put it G1. So it is your original plot multiplied by G. Yep. So this is now your new function, which you have compensated. Yeah. So next step, you can just do a root locus of this. Root locus of G1. So you have your root locus now, which is created. Now we want to overlay on that our again your damping ratio line at 0.5037. So again, still at damping ratio of sorry, overshoot of 16%. You just put a small value in actual frequency. Yeah. So let's find this point there. What is intersecting your damping ratio line and your locus? So you find that this point is if you look down there, it is at minus 3.395 and 5.817. Yep, so it's very close to, of course, you have worked with it's very close. It seems to be okay. Now, while you're doing that, you need to find a gain at this point. Yep. So you've got your target point now. I'll just say it to you. So it is your new operating point. Just find it out. Let me just find again on the graph. So same procedure we've seen earlier. So just put your cursor on that point there as close as possible. So let me just take this down. We're getting minus 3.3957 and 5.8013. Yep. So this is your operating point. So let's create a key now. Let's create T1. This minus at minus 3.3957 plus 5.8013i. Yeah. Now let's create our vector for poles. They are at 0. 0. You have minus 4 and minus 6. Now be careful. You if you look at your G1, you should just create it. Yeah, that's correct. So if you look at your I missed something. No, it's correct. So you have a pole at 0 and then a minus 4 and minus 6. That's correct. Now what I was trying to say now, your Z is not an empty because your Z actually is minus 3.37. So you have a 0 now. So you need to have a vector for your 0, and your T has been created as T1. So now we can call your K1 solving those also will be all this gain. So your P has been defined, your Z has been defined, and your T1 is the operating point that you went with. Yeah. So if we run that again as expected, your sum of angle is very close to minus 90 degrees, but we are doing that to get your T1. Yep. Now from here we can have we created GC already? Yes, we created GC already as your this is what we did to be able to get the step. So we have the closed loop as a function for the uncompensated system. Now we need to be able to get your your closed loop the compensated system. So if you call it GC1, yep. So it's going to be G1, which you have created already, times K1. Yep, because you found this K1. Divide by 1 plus G1 times K1. Yep, so it's your compensated system with your PD controller, and then you are finding your closed function with that, and then this is what you get. Let's do now two-step functions. So let's do the step of GC, and let's put it in red. Yep, so this is your initial uncompensated system, and now we just say hold on. And you do step now of GC1. So GC1 was your closed function as we calculated with your PD control. Just put that in. Yep. If we look at what you're getting, so this is your original system, and this is your new system, and the whole purpose was to reduce the settling time by 3. So you can see how it reduced. So you can ascertain now whether how far you can find out the new settling time and then compare it. Seems to be okay, and you can see your overshoot has more or less been maintained because we wanted to have 60% overshoot. So just to summarize, so I think the most important thing here is to be able to do a root locus, to overlay on the root locus your damping ratio line to get the operating point, and then use the function I've written for you, R locus gain, to get the gain. Okay, but you can also use the R locus gain function to get the sum of angles, which can be quite useful when you're designing the PD controller to get the sum of angles at a given operating point. Normally it's going to be minus 1 degrees if your point is already in the root locus, but when you're doing a PD controller design, if I new operating point, we know we don't get scientific ways. You get a sum of angle, and then you can determine what angle needs to be added by the zero to be able to achieve the new operating point. Now, once you do that, be very careful when you find the step response. Step response is always found on the closed loop transfer function. So you need to find your G over 1 plus GH, and then your G should be multiplied by G. And then that should be okay. Yeah. So I'm sending this video to you, and if you still got questions, so just you can drop an email and I can further.